it's a long process, and there's many different prototypes and iterations. I think that through the process of developing shader languages, generalizing those to vector languages, and then looking at different kinds of targets, including GPUs and the cell processor, and of course ordinary CPUs. And then we, went through Intel, and they got modified again. So I think we went through like 5 different iterations of the design. And so I think that you learn everything from every iteration. And initially, of course, we started with shaders before there were shaders. Okay, so our work in shaders predated things like CG and the OpenGL shading language. And that sort of evolved into a more SIMD style general-purpose programming language. But to say when it started, I guess the point is, when it started, it was a shading language. It was very specialized and narrow, and then it broadened. Well, let me recount the history then. So I've been involved in looking at how to express the vector capabilities of the hardware as a programming language for a while. And actually, since about 1999 is when I started getting involved in it. And we, at that point, started playing with these graphics accelerators, which at the time were actually graphics decelerators, because they actually made the machine slower. They weren't very, very efficient. But we started thinking of them as SIMD machines and started thinking about how to program them to do arbitrary operations beyond the scope of the original design. And we started designing languages for that. And that was the SH project. And SH actually included another concept, which was embedded domain-specific language. In other words, rather than designing a separate language for shaders, we actually embedded it in C++, using operator overloading and other tricks for code generation. So the SH project, which I wrote a book about, then evolved. We spun it off as a company. That company became RapidMind. RapidMind had a RapidMind platform, which was an evolution of SH into general-purpose computing, where we didn't focus just on shaders, but on the more general problem of vectorized coding and parallelization, actually. We looked at more targets than just GPUs. We looked at the cell processor, and we looked at Intel CPUs and AMD CPUs vector units. And that was the basis of that company's product. And when it was acquired by Intel, we merged that work with the CT project out of Intel Labs, and that became Array Building Blocks, the merger of those two streams. That was still an embedded C++ language. Array Building Blocks is now available as a What If project up on Intel. But one thing we discovered is that there were 2 concepts in SH, the vector parallelism and the embedded language. Unfortunately, we found that C++ syntax for embedding DSLs was too much overhead between, it was like 2 concepts at the same time, right? There was this DSL concept, and there was this parallelism concept. Both are powerful, but together the learning curve is too high to bring people into parallelism. So we actually decided to step back and look at less invasive ways to express parallelism with the same semantics. And if you look at the current Silk Plus product, that includes a lot of the concepts that were in ARB, but with a different syntax. So I still think that the embedded language approach is interesting, but the syntax can be a little confusing to people, so we actually stepped back from that a little bit. These high-level patterns we have elaborated upon over the course of evolution, and they still exist. Those patterns are consistent across all the languages we've studied, and we've discovered more. What's interesting is the number of patterns we've discovered has kind of converged to a relatively small set. And recently we decided to write a book called Structured Parallel Programming, which actually elaborates upon those patterns in a language-independent way. So the patterns are independent of the language. They're more conceptual in nature, and they're more ways of thinking about how to decompose a problem and how to express it in a way that's efficient. And there's kind of like grammatical rules where you can change the words, but the grammar remains the same, more or less. Well, I think the primary model that Intel is focusing on is actually Silk Plus, which gives you mechanisms for expressing vector parallelism both explicitly by actually doing array expressions, and implicitly by marking loops as being vectorizable, and then it goes and vectorizes them. That's the primary model. There are other secondary things that we've worked on. So if you go to what if, there's ISPC, which actually comes out of MATFAR, and it's a very interesting approach using what I call synchronous semantics. There's also ARB, which is actually has both the explicit array expressions and the implicit what I call a map operation way of expressing vectorization. But all those things actually appear now in Silk+. So I think that the answer to your question in terms of product is that Intel has the one product to express vectorization, and that's the Intel compiler, which includes extensions which are called collectively Silk+, to express both vectorization and parallelization. There's also TVB. TVB is very powerful. It's threading building blocks, but unfortunately it cannot directly address the problem of generating vector code, because vector code requires vector instructions, which TVB itself cannot generate. It has to depend on the compiler it's used with to generate vector instructions. So TVB is good at parallelization, but not at vectorization. The other thing you can do for vectorization is vector intrinsics, but because of the variety of instruction sets for vectorization, even just in Intel processors, we're trying to move away from intrinsics and to more abstract mechanisms like in Silk+. Right, so determinism basically means that every time you run it, you get the same answer. And this means that if you want to test code, you can basically test, did the code produce the answer that it produced last time, and was that answer correct? So you got to check if one answer is correct. Non-deterministic programs may generate different answers every time you run them. Now, each different answer may in fact be correct, but it's much harder to test because then you have to write a program that can prove that each different answer you get is actually correct. Of course, each different answer could also be wrong, or some could be wrong, which is actually an error. And the problem with that is that, you run it, maybe once in a while you get the wrong answer. That's not good either because testing becomes troublesome. You don't know, this test passed, maybe the next one won't. So determinism is a good property because you run it, you've tested it, it works, you're done. That said, there are performance advantages to non-determinism in some cases. And so the real challenge is really how to express controls for determinism to the user so the user can decide when and where to use non-determinism. And one thing that I'm constantly fighting is the assumption that it's okay to invisibly use non-determinism and get better performance. I think the right answer is the user has to decide when and where to use it. Sort of. So the issue is that floating point is not fully associative. In other words, you can't necessarily reorder the operations and say a floating point sum and get the same answer. And a lot of operations like reduction, like summing up all the numbers in a collection, assume associativity when you parallelize them. Now, the trouble is that some implementations of reduction use non-determinism to get better performance. So for example, you might break up the work if there's more processors available, but you may not break up the work in the same way depending on how many processors are available when you run it. And so then that changes the associativity every time you run the program and you get a different answer. That wouldn't be a problem for a truly associative operation like integer modular arithmetic. But it is a problem for floating point. So I think the right answer there is to provide two operations, a deterministic one and a non-deterministic one. Use non-determinism if your performance is the highest requirement, and what will happen is you'll get a slightly different answer in floating point precision every time you run it. And if you're okay with that, fine, and you want higher performance. But in some cases, you want exactly the same answer every time. And if you do that, the system should be able to constrain the ordering to do that, but the trade-off is you get lower performance.